All right, so you remember in section 3.2, which we talked about last time, then we introduced confidence intervals. And confidence interval was, or the purpose of a confidence interval was to estimate the value of a parameter. So we wrote that down last time, but I'm just going to refresh our memory by writing it down again. And we talked last time about the basic format for our confidence interval. So the basic format is to have a sample statistic plus or minus the margin of error. All right, we learned how to construct confidence intervals. We talked a lot about how to get the margin of error. We said that margin of error is based on the standard error. And remember, standard error is just the standard deviation of the sampling distribution. So kind of where we left off last time, we said, okay, we want to create a confidence interval. A confidence interval is this plausible range of values for a parameter. And in order to do that, we're going to create a sampling distribution. And we create a sampling distribution by taking many, many random samples from the population, computing the sample statistic for each of those samples, and then using the variation of that sampling distribution, which we call the standard error, to construct our confidence interval. And we said if we want to create a 95% confidence interval, all we have to do is take our sample statistic plus and minus 2 times the standard error. And again, the standard error came from that sampling distribution. So that's kind of where we left off last time, but we noticed one small problem with this method. And anybody remember what our one small problem was? So basically, if you look at our plan here, our plan says we have to take many random samples. And when we were creating those sampling distributions, many was thousands. So we're talking about thousands of random samples from the population. But in real life, do we take thousands of random samples from the population? No way, right? We don't have nearly enough resources to be able to do all that. So in real life, we only get one sample, and we have to be able to do something with that one sample. So how are we going to be able to estimate the variability of the sampling distribution if we only have one sample? That's what we're going to answer today. We're going to figure out how to be able to figure out how much sample statistics vary if we only have one sample. And to do that, we're going to use this really cool method called bootstrapping. So if you've taken statistics before in the past, it is very likely that you've never heard of bootstrapping. It's not that it's a newer technique, it's been around a while, but it relies heavily on computers being able to do a lot of the work for you. So, you know, back in my day when I was taking this class in college, like a long time ago, 25 years ago, then we didn't use bootstrapping because it would have required a lot of computer power. And in fact, I actually did use bootstrapping when I wrote my master's thesis, and it required pages and pages of code in order for me to use bootstrapping. But fast forward to today, 25 years later, and now we have resources such as StackKey that can easily do bootstrapping for us, which is going to make this a much more viable technique for our day, for the modern day. And it is, I think it's really cool. So let's talk about the general idea behind what bootstrapping is. Basically, when we take a random sample from the population, if we're using a random method to select that sample, then we're assuming that our sample is representative of the population. You could even think of the sample as being like a mini version of the population. So if our sample is like a mini version of the population, then if I were to take my sample and imagine making lots and lots of copies of my sample, that would sort of, kind of, imitate what we think the population looks like. So if my sample is representative, if I was able to actually just make a whole bunch of copies of my sample, then that might mimic what the actual population looks like. Of course, doing this, what we have to assume is that we are taking random samples because the only way we're going to get an unbiased sample is by using a random method to select our sample. So here's kind of a graphic look at that. Okay, so let's say I take a random sample, one random sample from my population of 6 people. So these are the 6 little stick figures that I've selected from my population. So if I've used a random method, then we're assuming that these 6 people are representative of the whole population. And if that's the case, then the population might just look like lots and lots of copies of my sample. So here's a whole bunch of copies put together of my sample. So I've just taken my sample and I've copied it a whole bunch of time. All right, so now if I have all these copies of my sample, this is like a simulated population. And now that I have this simulated population, I could take samples from this simulated population. From each of those simulated samples, I could calculate a sample statistic, and then I could see how all those statistics varied, and that should be similar to what the actual sampling distribution looks like. So this is kind of the basic idea behind what we're doing when we're doing what we call bootstrapping. Okay, so in a bootstrap situation, we're trying to capture this idea of, okay, if I were to make lots and lots of copies of my original sample and call that my simulated population, then if I were to take samples from that, lots of samples, thousands of samples, from each of those samples, we're going to call those bootstrap samples. From each of those bootstrap samples, we're going to calculate our sample statistic. So we're going to call that bootstrap statistic. And then we're going to look at the distribution of those bootstrap statistic values. And that should be very similar to our sampling distribution. And we've managed to do all of that by only taking one real sample from the actual population. Now, in real life, then we don't actually make lots and lots of copies of our original sample. Instead, what we're going to do is we're going to sample with replacement from the original sample. If we sample with replacement from our original sample, it's essentially the same thing as making lots and lots of copies and then sampling from that giant copy thing that we created. So if I sample with replacement, like if I look back up here, you know, if I have lots and lots of copies, if I'm taking a sample from here of 6 people, then would it be possible for me to get the grumpy, red-haired, no-arm, skinny person more than once? Yes, okay, because there's more than one of those people in here. So if I was taking a sample of 6 people, it would be possible for me to get the same person more than once, even though in my original sample, that person is only there one time. So we get that same idea by sampling with replacement. So by sampling with replacement, what we're going to do is we're going to start with our original sample, and whatever the size is of our original sample, that's what we want to make our bootstrap sample. So if my original sample was 6, sample size was 6, then my bootstrap sample also needs to have a sample size of 6. So I'm going to pick a person from my original sample, write down their value, put them back in, select again, write down that value, put it back in. I'm going to do that 6 times. Every time I'm putting the person back in, so there's a chance that they could be selected again as part of my bootstrap sample. All right, once I've gotten up to my sample size of 6, that's when I'm going to calculate my sample statistic, and then put that one aside so I can start the whole process again and do that a few thousand times. All right, so we're going to simulate a sampling distribution by taking repeated random samples from this population that's created by taking multiple samples. But really what we're going to be doing is we're going to be sampling with replacement from our original sample. That's going to get us basically the same thing. So here's my original sample was these guys. If I'm sampling with replacement, then here is what a possible bootstrap sample might look like. It is possible to get more than one of the same person in your bootstrap sample, and that's okay. So here's kind of a general breakdown. I have a couple slides that are going to show us the general idea of what we're doing, then we're going to write down some definitions. So we start with our original sample. Remember that the original sample was randomly selected from the real population. So I take my one original sample, randomly selected from the real population, and from that, I'm going to calculate my sample statistic. My sample statistic is the best estimate for the population parameter. So this sample statistic calculated from my original sample is still going to be at the heart of my confidence interval. Okay, next, I need to figure out what kinds of samples are possible and how they vary. That's when I'm going to start bootstrapping. So what I'm going to do is I'm going to take lots and lots of samples by sampling with replacement from my original sample. From each of those bootstrap samples, I'm going to compute a bootstrap statistic, and then I'm going to look at the distribution of all those bootstrap statistics, which is called my bootstrap distribution. Okay, here's another way to look at it. So remember, our end goal is to get a confidence interval, and we said a confidence interval is a statistic plus and minus a margin of error. So again, I start by taking one real sample from the real population. So this is my one shot, my one real sample. From that sample, I'm going to calculate my sample statistic. That is the sample statistic that we're going to use to compute our confidence interval. Then I'm going to take a whole bunch of bootstrap samples. So the bootstrap samples are taken by sampling with replacement from my original sample, and the bootstrap samples are going to be the same sample size as my original sample. Once I have all these bootstrap samples, and really we're going to do this thousands of times, then we're going to calculate the sample statistic from all those bootstrap samples. So if I'm originally looking at a sample mean, then from each of my bootstrap samples, I would calculate a sample mean. If I'm originally looking at the sample proportion, then from each of my bootstrap samples, I would calculate the sample proportion. This works for anything. It works for correlation, it works for difference in proportions, difference in means, all of the things that we've been looking at so far. All right, then once I've got the statistics for each of those bootstrap samples, I'm going to construct my bootstrap distribution. And my bootstrap distribution is intended to mimic what the sampling distribution might look like. And the reason for that, the reason why we need that is so we can estimate the standard error. So I'm going to use the standard deviation of my bootstrap distribution as my standard error to construct my confidence interval. So once I've got my bootstrap distribution, I get the standard error from the bootstrap distribution. And if I want a 95% confidence interval, then my margin of error is just going to be 2 times the standard error. I plug that in over here, and ta-da, I finally have my confidence interval. All right, so let's write down some of those definitions. All right, so let's define bootstrap sample, bootstrap statistic, and bootstrap distribution. So starting with bootstrap sample. So a bootstrap sample is a sample obtained by sampling with replacement from the original sample using the original sample size. So remember, the original sample, that was sampled from the population, but these bootstrap samples were sampling from the sample. So next term is the bootstrap statistic. So our bootstrap statistic is the sample statistic calculated from a bootstrap sample. And then finally, we have our bootstrap distribution, which is the distribution of bootstrap statistic values. All right, and I'll just put in parentheses that it's the standard error of the bootstrap distribution that we're going to use to estimate the standard error in order to construct our confidence interval. So we'll use the standard deviation of the bootstrap distribution to estimate the standard error and construct the confidence interval. All right, so let's talk a little bit more about bootstrap and bootstrap distributions, bootstrap samples. Starting with why bootstrap? Like where does this term bootstrap come from? And basically it comes from an old saying that was pulling yourself up by your bootstraps. And that saying was supposed to mean lifting yourself in the air simply by pulling on the laces of your boots, which is impossible. Like if you're pulling on the bootstraps of your boot, you can't actually lift yourself in the air. So if you could pull yourself up by your bootstraps, then you would be accomplishing an impossible task without any outside help. And that's where the name of this method came from, because that's kind of what we're doing. So here, what we need to do is we need to create this sampling distribution, which is based on thousands of samples. And instead, we only have one sample, but we are going to be able to use that one sample to help us mimic the sampling distribution and be able to construct our confidence intervals. So we're going to be able to accomplish this impossible task of estimating the variation of lots of sample statistics just by using our original sample. So let's look at a few of these things and see if they are possible bootstrap samples. See if we can test your knowledge of bootstrap samples. So if your original sample has data values 18, 19, 19, 20, and 21, is the following sample a possible bootstrap sample? So could I get 18, 19, 20, 21, and 22? Okay, I'm seeing lots of no's. So why not? What's wrong with it? Okay, good. So the 22 is what's wrong with this one. So we're sampling from our original sample. So if the original sample doesn't have a 22, then neither can the bootstrap sample, because we're sampling from that. So nope, that one's not valid. How about this one here? So my original sample, same 18, 19, 19, 20, and 21. Then is this a possible bootstrap sample, 18, 19, 20, 21? All right, I'm seeing some yeses and some no's. The answer is no, because, okay, now I'm getting everybody putting their reasoning in there. So the answer is no, because the bootstrap sample has to be the same size as the original sample. So if my original sample had 5 values in it, then my bootstrap sample also has to have 5 values in it. Okay, here's another one. Is this one possible? 18, 18, 19, 20, 21. Yes, this one is possible, because even though there's 2 18s, since we're sampling with replacement, it is possible to get more than one of the same value from the original. So this one's a good one. Okay, now suppose you have a sample of size n equals 50. That's our real sample. You sample with replacement 1,000 times to get 1,000 bootstrap samples. What would be the sample size of each bootstrap sample? Would it be 50 or 1,000? Good. So our bootstrap sample is going to be the same size as the original sample. So if the original sample had 50, then our bootstrap samples are also going to have 50. Okay, same scenario. This time we want to know how many bootstrap statistics will you have? Good. So we're going to have one bootstrap statistic for each bootstrap sample. So if I took 1,000 bootstrap samples, then I'm going to have 1,000 bootstrap statistics. So remember that the sample size is different from the number of samples. All right, next we're going to fill out this little chart. The whole point of a bootstrap distribution is to mimic the sampling distribution so that we can use that estimate for standard error to construct our confidence intervals. So we're going to talk about the similarities and differences between sampling distributions and bootstrap distributions, starting with the shape. So first of all, when we talk about sampling distributions, what shape did we say that sampling distributions were? We said if our sample size is large, the shape of the sampling distribution will be bell-shaped symmetric. Exactly. So I'm going to say if n is large, then bell-shaped symmetric. When we think about our bootstrap distribution, same scenario. So if our sample size is large, then the bootstrap distribution will also be bell-shaped symmetric. All right, what about the center? Okay, if we use a random method to select our sample from the population, we said the sampling distribution is centered on what? This is something we talked about in section 3.1. So if we use a random method to select the sample, the sampling distribution, so the distribution of lots and lots of sample statistics, is centered on the population parameter. Exactly. And that population parameter could be the population mean. It could also be the population proportion, the population correlation, difference in means, difference in proportions. So whatever it is that we're measuring or trying to estimate actually is going to be what it's centered on. Now our bootstrap distribution, so backing up, our sampling distribution was created by taking lots and lots of samples from the population. So because we're taking random samples from the population, that's why it's going to be centered on the population parameter. Our bootstrap distribution is created by taking lots and lots of random samples with replacement from our sample. So our bootstrap distribution is going to be centered on the value of the original sample statistic. So the center of the bootstrap distribution is going to be the same as the original sample statistic. All right, what about the spread? When we talk about the spread of the sampling distribution, the variation of the sampling distribution, we gave it a special name. We even gave it a special acronym. What did we call it? So it's the same thing as the standard deviation of the sampling distribution, only we gave it a special name when we're talking about sampling distributions. Yes, the standard error. So the spread of the sampling distribution is what we call the standard error. And the acronym that we have for that is just SE. All right, and for the bootstrap distribution, the whole reason why we're constructing the bootstrap distribution is to mimic the variability of the sampling distribution. So the bootstrap distribution does have variation very, very similar to the standard error. So I'm going to say similar to the standard error of the sampling distribution. So the bootstrap distribution is going to have variation that is very similar to the standard error of the sampling distribution. Okay, and then last question, as we're constructing these sampling distributions, then we often look at a dot plot. You could also look at a histogram, but in our class, we're going to look at dot plots a lot when we're talking about sampling distributions or bootstrap distributions. So I want to know, what does one dot equal, or what does it represent on a sampling distribution? So on a sampling distribution, one dot is equal to the value of what? Anybody remember? Good, yeah, a sample statistic, which that sample statistic could be a sample mean, but it could also be a sample proportion or sample correlation, depending on what we're measuring. So one dot on a sampling distribution is one sample statistic. All right, and on a bootstrap distribution, remember we're taking lots and lots of these bootstrap samples. From each of those bootstrap samples, we're calculating a bootstrap statistic. So a bootstrap distribution, one dot is one bootstrap statistic. And it's important to realize that these are different from each other. So one sample statistic means that we took an actual sample from the actual population and we computed the sample statistic value. When we're talking about a bootstrap statistic, we didn't take an actual sample. We took a sample from our sample. So it's like a resampled kind of sample. So it's different than a regular old statistic from a real sample. Okay, so looking at these four things that we evaluated, which things are the same from the sampling distribution and the bootstrap distribution? So which things do they have in common? Are they the same? So shape is one of them. So shape is the same and spread is the same. And then the other two things are different. So it's important to know what's the same and what's the difference between these two distributions. All right, so let's look at an example how we're actually going to use this. And there's actually two different methods that we're going to use, where we're going to use the bootstrap distribution to help us create a confidence interval for the parameter. So one of the methods is called the standard error method, and the other method is called the percentile method. So first we're going to talk about the standard error method. And this one should feel pretty familiar to you because it's basically the same thing that we did in section 3.2, only instead of using the standard error from our sampling distribution, we're going to use the standard error estimate from our bootstrap distribution. So let's write down the steps for constructing a confidence interval using what we call the standard error method. So first thing, before we write down the steps though, there's one condition to using this method, and that is that the bootstrap distribution has to be bell-shaped symmetric in order for this to work out. So our condition is that the bootstrap distribution must be bell-shaped symmetric. All right, so if our bootstrap distribution is bell-shaped symmetric, then this is how we're going to construct a confidence interval using this standard error method. So the first thing that we would do was take a sample, take a real sample from our real population. So I'm going to say take a random sample from the population. Once we've taken our random sample from the population, we're going to compute the sample statistic. And remember, we keep calling the sample statistic the best estimate for the parameter. Once we've computed our sample statistic, the next thing we're going to do is we're going to use stat key to construct a bootstrap distribution. So we're going to use stat key to take lots and lots of bootstrap samples, calculate all those bootstrap statistics, and then come up with this lovely bootstrap distribution. So use stat key to construct a bootstrap distribution with several thousand samples. Then we're going to use the standard error from the bootstrap distribution to construct our confidence interval. And we're going to construct that confidence interval pretty much the same way we were doing it in section 3.2, where we're going to take our sample statistic, and I'm going to put original here, just to remind us that we want to use the value that was originally calculated in step 2. So my original sample statistic plus and minus 2 times the standard error. And before we try it out, I'm just going to tell you one caution. This is something that I see done wrong a lot on exams, like a lot, like sometimes more than half the people get this wrong. And that is that I want you to use the original sample statistic when you're constructing the confidence interval. Do not use the mean of the bootstrap distribution. We did mention that the center of the bootstrap distribution should be the same as the original sample statistic, but that also depends on, it's not going to be exactly the same because we're only taking a few thousand samples and not every possible sample that could be computed from that. So because we only have a few thousand, the center of that is going to be more of an estimate, and we want to use the original sample statistic because it's still the best estimate for the population parameter. So my caution is use only the original sample statistic to compute the confidence interval. Do not use the mean of the bootstrap distribution. And right now you're probably thinking, oh, I don't know why people get that wrong. That seems so obvious. But as we get into this and you start doing some examples, you're going to see why it is tempting to use the mean of the bootstrap distribution. All right, so we're going to look at an example. So this first example is about used Mustang cars. So we want to know what is the average price of a used Mustang car. And a random sample of 25 Mustangs from autotrader.com was selected, and the price in thousands for each car was recorded. So first thing we want to know is what is the population? So what do you think? What's the population that we're interested in by conducting this study? Perfect, all used Mustangs. So the population is all used Mustangs. All right, so that's our population. What about our sample? What's the sample that we're using here? The sample is going to be the 25 Mustangs that were randomly selected. So the sample is the 25 Mustangs that were randomly selected. All right, next question is what is the population parameter? So this is the thing that we are trying to estimate. And when we're defining the population parameter, it's going to involve a symbol and a definition written out in words in the context of the problem. We're not going to have an actual value for the population parameter because if we had the value, we wouldn't need to do a confidence interval. So we're never going to have, when we're doing a confidence interval, we're not going to have the actual population parameter. So that would defeat the purpose of doing a confidence interval. All right, so the symbol, seeing lots of those over there, is going to be mu. Okay, and I can tell that because if I look at my study here, I measured one variable, the price in thousands, and that one variable is quantitative. So if I have one quantitative variable, then I'm interested in the mean. So one population mean. And the symbol for the population mean is mu. So now I'm going to write out what mu is in words. So the very first thing that should follow the equal sign is a one-word description of what mu is, which is a mean. So it should say mu equals the mean. And what is it the mean of? It's the mean price for all used Mustangs. And remember, this is the population parameter. It's a number that describes the population. So somewhere in your wording, you should be using whatever you said the population was. So we said the population was all used Mustangs. So when I'm writing out my thing in context, it should include whatever I said the population was. All right, so my population parameter is mu. Mu is the mean price for all used Mustangs. Now let's talk about the sample statistic. So first of all, let's talk about the symbol for the sample statistic. And if my population parameter was mu, what's my sample statistic? X bar. So remember, the population parameter and the sample statistic, they go hand in hand. If you figured out which parameter is the correct one, then you should know exactly which sample statistic is the correct one. Mu goes with X bar, P goes with P hat, rho goes with R, etc. So the symbol for our sample statistic is going to be X bar. With the information that I have so far, I don't know what the value is, but if I can get a hold of that sample of the 25 Mustang car prices, then I could compute that sample mean and I would have a value for my X bar. So that is what I'm going to do here. So here is sample of 15 used Mustangs. And if we find the average of all 15 of those used Mustangs, then here's what I get for my sample statistic. And remember, they're listing the price in thousands, so this is really $15,980 if we're converting that back to dollars. So X bar equals 15.98 is my sample statistic. All right, now I'm ready to go ahead and construct my confidence interval using the standard error method. So we're gonna bootstrap to figure that out. So we start with our original sample. We're going to sample with replacement from that original sample to come up with a bootstrap sample. That's what that little animation was about. We're going to calculate the mean price of my bootstrap sample, and then I'm going to repeat that many, many times, like thousands of times. So I'm going to show you how to do this inside of StatKey here. So share my screen. I got to go figure out where my StatKey tab is. There we go. Okay, and inside of StatKey, first of all, notice that this whole center section on the top here is for bootstrap confidence intervals. So this is where we're going to be in section 3.3 and 3.4 is right here. And if you can figure out what you measured and what type of variables you have, then you can figure out what type of confidence interval that you want to use. And you notice that the way this is set up in here is that everything kind of goes together on the same row. So if I have one quantitative variable, that means I'm doing a confidence interval for a single mean or median or standard deviation. In our class, we're really just going to do means. There might be something in the, I can't remember, there's a Wiley Plus problem that might have you do something different, but not the written homework and not on exams. I would just do mean here. So if I have one quantitative variable, then I would choose confidence intervals for a single mean. If I have one categorical variable that I measured, I would do a confidence interval for a single proportion. If I had one quantitative and one categorical variable that are measured, then I'm going to do a confidence interval for the difference in mean. So you can see how these match up to each other and help make it easier to figure out which is the right one. And in our case, we measured one quantitative variable, so I'm going to click on confidence interval for a single mean. And if you guys want to do this along with me, you're welcome to to do it. I'm going to give you a practice problem to work on in just a second, so you'll get a chance to try it on your own if you don't do it now as well. All right, so once I'm in here, notice in the upper right-hand corner here, I have all the information on the original sample. So this is my random sample from the population. It tells me that the mean was 15.98. That's my sample mean, X bar. It tells me all the median, standard deviation. It tells me my sample size here, and it even gives me a lovely little dot plot of my sample values. Now I'm ready to create a bootstrap distribution. So I'm going to click on generate one sample to begin with, just so we can kind of see what it's doing here. So this one dot over here, now you can see the bottom right has something showing up there, means that we took a sample with replacement from our original sample. And if you click the show data box, it'll even show you which values were included in this resample, so this bootstrap sample. It tells you the mean of the bootstrap sample and all that kind of good stuff. It does a nice little graph there. So that's one bootstrap statistic that we've plotted here on our graph. It's actually one bootstrap mean because we're looking at the mean in this particular data set. So now I want to do this a whole bunch of times. When you're doing your Wiley Plus homework, you want to do this thousands of times, like upward of like 10,000 or more times, because you'll notice as you keep clicking on this generate 1,000 samples button, then things kind of stabilize over here in the upper corner as far as standard error goes and the mean there. And so we want kind of to get to the point where we're seeing very similar values as we click on this. All right, once we've done it several thousand times, then the standard error that's in this upper corner here, that's the number we're going to use to construct our confidence interval, along with the original sample statistic. Okay, this is where I'm going to tell you about that caution. Remember I said the caution says use the original sample statistic, that's this mean equals 15.98 for this sample, not the mean of the bootstrap distribution. So many of you will be tempted to use this mean from the bootstrap distribution. Notice it's very close, but slightly different from the original sample statistic. So the original sample statistic is our best bet because it is the best estimate of the population parameter. Do not use the mean from the bootstrap distribution. We are going to use, however, the standard error from the bootstrap distribution. So going back to my presentation here, I have a bootstrap distribution that I already constructed here. And so now we're going to use, I'm going to use this one for my example here. I'm going to use the standard error from my bootstrap distribution and the mean of my original sample to construct my confidence interval. So to create a 95% confidence interval, I'm going to take my statistic plus or minus 2 times the standard error. That's going to be 15,980 plus or minus 2 times 2,178. Multiply that out, I get this 4,356. What is this number? What's another name for this number, the 4,356? What do we call that number? Yeah, that's the margin of error. So I've used the standard error to create my margin of error. I'm going to add and subtract that margin of error. That's going to give me my confidence interval. Now that I have my confidence interval, I can interpret this just like we talked about in section 3.2. So I would say we are 95% confident that the average price of a used Mustang on autotrader.com is between $11,624 and $20,336. All right, questions on how we did that or where any of these numbers came from? Anything like that? All right, let's look at another example. So this one is also about cars, but it's a little bit different data that's collected this time. So 20 car models were selected at random from kellybluebook.com. The original price in dollars and the value after the car has been driven 10 miles were recorded for each model. And the depreciation is the difference, taking the new price minus the used price. And what we want to find out is what is the mean depreciation for all car models. So we'll talk about the first few of these questions, and then I'm gonna let you go to StatKey on your own and see if you can come up with the confidence interval. But in my classes yesterday, people were a little bit confused about what we were measuring here. So let's talk about this together. So first of all, the population. What's gonna be the population here? What's my entire group of interest? So what's everything I wanna draw conclusions about? All right, well, look at what we measured here. What were we taking measurements on? Car models, right? So if we took measurements on car models, then our population is going to be all car models. So all car models is our population. All right, next let's look at our sample. So what did we actually measure in this case? So our population is all car models. The sample is the 20 car models that we actually took measurements from on kellybluebook.com. All right, so next let's talk about the parameter, okay? And it says that we looked at the original price and the price after they drove it off the lot, basically, and they essentially wanted to know the depreciation. So the depreciation was calculated as the difference between the new price and the used price. So is depreciation, is that a categorical variable or a quantitative variable? Quantitative, exactly. So this is a quantitative variable. So we have one quantitative variable that we measured on these car models, which is depreciation. So for one quantitative variable, my population parameter is going to be mu. And what's the first word that should follow the equal sign here if my parameter is mu? Mean, exactly. So mean what? Well, we measured depreciation, so it's the mean depreciation for, okay, and this is where I fill in what my population was. So what did we say our population was? We said our population was all car models. So mu is the mean depreciation for all car models. All right, so we are looking at, again, one quantitative variable here. So now what I want to do is I'm going to give you a couple minutes. I want you to go into StatKey. And if you look in the, let me find my StatKey. If you look in the drop-down menu here, you'll notice that the car depreciation data is in here. So go to StatKey, click on the confidence interval for a mean, choose the car depreciation data, and then I want you to construct a confidence interval. So first you can find the sample statistic. Remember where to find the sample statistic. Then we're going to generate a bunch of bootstrap samples, and then we're going to use the standard error and the original sample statistic to construct a confidence interval. So I'm going to give you just a couple minutes, 2-3 minutes, to see if you can do that on your own computer, and then we'll look at it together. When you've got your confidence interval, you can go ahead and put it in the chat window, keeping in mind that all of us are probably going to get slightly different confidence intervals. They should be similar, but they're going to be slightly different depending on what standard error estimate you got from your bootstrap distribution. All right, looks like a bunch of people have answers over there. So basically your process here, we're going to create our bootstrap distribution by clicking on this generate 1,000 samples button a whole bunch of times. We've done that several times. Then we're going to use the standard error estimate up in this upper right-hand corner of the graph. And we're going to add and subtract 2 times that value from the mean of our original sample, so the 2355. So I did that over here. And for mine, on this one that I did prior to class, I put it in my presentation, I had a standard error estimate of 185.329. So I multiply that by 2, add and subtract that from my original sample statistic. So again, use the original sample statistic value. Do not use the mean of your bootstrap distribution. Maybe like write that on your notes somewhere really big. If we were taking a paper test, then I would tell you, hey, as soon as you do your paper, just go through your test and cross out any of those means, so you're not tempted to use them. You're actually not ever going to really need to use that value that's in the upper corner there for the mean. So I'm going to use my standard error estimate, add and subtract. So when I did mine, I got an interval that went from 1985-ish to 2726-ish, which is pretty close to what I saw all of you guys getting over there in the chat window. So we'd say we're 95% confident that the true mean car depreciation for all car models is between, on mine I would say $1,985.19 and $2,726.51. All right, questions so far, or questions on how we're going to use that standard error method? Thumbs up if you were able to get something, even if you didn't type it in the window. Okay, awesome. All right, so now we're going to talk about the other method that we can use. So for the standard error method, the one that we've learned so far, there's a couple of restrictions on it. First of all, you have to have a bell-shaped symmetric distribution, and this method only works if you want to do a 95% confidence interval. But what if your bootstrap distribution is symmetric, but it's not bell-shaped? Or what if you want to use a level of confidence that's not 95%? Maybe you want a 90% confidence interval, or a 99% confidence interval, or any other level of confidence besides 95%. Well, we have another method that we can use based on bootstrap distributions that can be used in any of these scenarios. So when we have not a bell-shaped distribution, or if we want to construct a confidence interval with a confidence level that is different from 95%. So this method, the second method, is called the percentile method. And it basically says that if the bootstrap distribution is symmetric, then we can construct a confidence interval by finding the percentiles in the bootstrap distribution so that the proportion of bootstrap statistics between those percentiles matches the desired level of confidence. This definition is already written on your notes page if you're using my notes page. So let's just refresh our memory a little bit as to what actually a percentile is. We defined this back in section, I don't know, 2.2 or 2.3. I think it was 2.3. But let's kind of refresh about what a percentile is. So the pth percentile is the value of the variable which is greater than p% of the data. So the pth percentile is the value of the variable which is greater than p% of the data. Or another way to look at the percentile is that p% of the data are below that value. So the key thing to remember here is that the percentiles of a distribution are actual values of the variable. The percentiles are not the percents themselves. They're the values of the variable that correspond to a certain percentage of the data being below or above that value. So in other words, like let's say you take the ACT and you find out that you get a score of 29 and they tell you that you're in the 92nd percentile. Okay, so if you're in the 92nd percentile, then your score 29 would be the 92nd percentile, meaning that 92% of the people scored 29 or lower, and then 8% of the people scored above 29 on the value. So the percentile itself is the value of the variable, not the percentage. So keeping that in mind, I have a little graphic here. Whoops. To help us understand what we're doing when we're doing the percentile method. If I can get my slide to change, it doesn't want to. There we go. Okay, so our bootstrap distribution, most of the time it's bell-shaped symmetric, so it could be, if we kind of smoothed out all those dots, it might look something like this. And the observed statistic, our original sample statistic, is what's going to be in the center of our bootstrap distribution. So when we're trying to construct a confidence interval using the percentiles, what we want to do is we want to get P% of the dots, if we're using a dot plot, which we pretty much are in this class. So we want to get whatever our confidence level, so if our confidence level is 95%, we want 95% of the dots right in the middle of the distribution. And then where we would make that cutoff so that exactly 95% of the dots are smack dab in the middle, those cutoff values are going to be our upper and lower bounds of our confidence interval. So the percentile method, we're going to keep P% of the, let's see, for a P% confidence interval, we're going to keep P% of the bootstrap statistics in the middle of the distribution. So if I'm doing a 99% confidence interval, I'm going to keep 99% of the values in the middle, leaving 0.5% in each tail. So that means that the upper and lower bounds of my confidence interval would correspond to the 0.5 percentile and the 99.5 percentile of that distribution. So that's basically where this method gets its name. So in practice, when we're doing this in StatKey, you're going to love this method in StatKey because it's actually even easier than doing the standard error method. But what we're going to do is we're going to go, so I'm going to go back to StatKey so I can show this to you here. All right, so I'm going to do it for, I'll do it for the Mustangs. Okay, so here's my Mustang data. I'm going to generate my bootstrap distribution just like I did before. Now to use the percentile method, once I've generated my bootstrap distribution, I'm going to click on the two-tail button up here in the left-hand corner. I'm going to make sure this center box has the value that corresponds to my confidence level. So if I want a 95% confidence level, then I want this to say 0.95. 0.95 is actually the default, so it already said 0.95 when I clicked on it. But if you wanted to change this to 0.99, 0.90, 0.98, whatever the problem's asking you for, you can change that here. Once you do that, so I clicked on two-tail, I made sure this corresponded to my confidence level. These two numbers down here at the bottom, that's the upper and lower bounds of my confidence interval. So there's not even any calculations. There's just this magic button that you click, the two-tail button, and then as long as you make sure that center box has your confidence level in it, these bottom two numbers are your confidence interval. So I have that here. Here's the Mustang data. Again, I was doing a 95% confidence interval here. And with the distribution that I had in my slideshow here, my confidence interval went from 11.932 to 20.474. So I would just say we're 95% confident that the true mean price of a used Mustang is between $11,932 and $20,474. So pretty handy dandy, right? All right, so I want you to go back to your car depreciation data that you had and see if you can use this method to construct a confidence interval. And if you still have your distribution up, so you didn't get rid of it from when we just did this example a second ago, then all you have to do is click on that two-tail button, make sure it says 95 in the middle, because we're going to still do a 95% confidence interval there. All right, and you don't have to type it in the chat window box, but you should end up getting something close to what I've got here, like 2006-ish to 2736, somewhere in that neighborhood. And it should be fairly similar to what you got when you used the standard error method. So if I go back to my presentation here, so back on the Mustangs, then using the standard error method, I got this interval that went from 11,624 to 20,336. And using the percentile method, I got 11,932 to 20,474. 474. So you can see that you get very similar answers using the standard error method versus the percentile method. So really you can choose either method that you like best in real life. In our class, you should obviously do the one that's specified in the problem. But in real life, you could use either method, defaulting to the percentile method if you want a confidence level that is other than 95%. Now, let's talk about what you're going to do on the exam, however. So on the exam, you're not going to have stat key. There is going to be no magical button that you can click that will shade the little red areas in and tell you what the confidence interval is. So instead, you're going to be given a bootstrap distribution, like a picture of a bootstrap distribution, and you're going to have to use that to come up with your confidence interval. So this is how we can do the percentile method by hand, okay? So essentially what we're doing here is the same thing that happens when you press that to tail button, but we're gonna have to count the dots to figure out where to draw those lines, where the difference between the red and the black dots is, essentially. So we have this handy dandy little formula that we can use to figure out how many dots that we need to count over. It's gonna be based on the number of samples in your bootstrap distribution, which you can get by looking in the upper right-hand corner of the distribution. And it's also based on your confidence level. And when you plug your confidence level into this formula, we're always gonna use the decimal form. So we're gonna have, if I'm doing a 95% confidence interval, it'll be 1 minus 0.95 over 2. Once you come up with the correct number of dots, then we're gonna start on the left, count over that many dots, draw a line. Wherever that line crosses the x-axis, that value is your lower bound of your confidence interval. Same thing coming from the upper direction. So I'm going to start from the right, counting over that many dots, draw a line. Where that line crosses the x-axis is the upper limit of your confidence interval. So let's look at that again for this card appreciation data. So this is the graph that's on your paper. I think it's on your notes pages. Yeah, should be the same one that's on there. So we're gonna try now using the by hand percentile method to construct this. So I still want a 95% confidence interval. So I need to look at how many samples I have and use that to figure out how many dots I need to count. So looking at my formula here, I'm gonna have the number of samples, which is 1,000, times 1 minus my confidence level, which was 0.95, divided by 2. So plug those numbers into your calculator and make sure that you get 25 as the answer. Because I do see a lot of people that have problems plugging this into their calculator correctly. Your calculator often is going to use correct order of operations. So you might have to use parentheses if you're putting it all in, or you might have to do it in parts to make sure you get that answer. So if you don't get 25 out when you do it, hang out after class for a second and we'll look at what you're doing and how you can do it so that you make sure the right order of operations is being used. All right, so 25 dots is what I got here. So to construct my confidence interval, I'm gonna start over here on the left-hand side and I'm gonna count 25 dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay. And where that is, you're gonna draw a line if you're doing this on your paper. So that was here. So I drew my line there. Okay, where my line crosses the x-axis is the lower limit of my confidence interval. So looking at my grid lines here, I can see that I'm not exactly on the grid line, which would be 2,000. I'm a little bit over. I can see that there is 100 values, 100, the tick marks are every 100. So based on where I cross the x-axis there, I think that's about 2010. So the lower limit of my confidence interval would be 2010. Now I'm gonna do the same thing, but coming from the right. So I'm gonna count over 25 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so, So then I'm going to draw another line there. Okay, and again, where that line crosses the x-axis is where I'm going to draw my, or call my value. Oh, and I think I said that there was 100 values in between tick marks before, but that was not correct. There's actually 200 values in between tick marks. So I can see here's the 2600 tick mark, here's the 2800 tick mark. This one's in the middle, little to the right of the middle. So I'm going to call that 2720. So, and maybe I should have called this one 2020. You can see that it's a little bit of guesswork here. You're trying to make the best estimate on that value based on the tick marks that are on the graph and everything. As long as you're in the realm on the exam, then you'll be good. On your Wiley Plus homework, use the two-tail button every time. On your written homework and on the exam, like I said, as long as your answer makes sense based on where you drew your lines and how many dots you had, then you'll be fine. So that's going to be the upper value of my confidence interval. So I'd say we're 95% confident that the true mean car depreciation is between $2,010 and $2,720, $2,720. All right, so doing it by hand is a little bit more complicated, but not too bad. And I actually kind of like it because it really helps you understand a little bit more what that magic two-tail button is doing when you click on it. All right, questions on how to use this method? All right, we have one more example that we're going to look at here. So far we've only looked at 95% confidence intervals, but what if we want to be more confident than 95%? Well, we can do that using the percentile method. We can have any level of confidence that we want to. So this next data set was collected on 50 healthy adults, and they measured a whole bunch of variables, including body temperature. And what we want to know is the mean temperature for all healthy adults. So population is going to be all healthy adults. The sample, the subset of the population that we're actually measuring is going to be these 50 adults that we actually measured. So the 50 healthy adults. Our population parameter, we're looking at, looks like we measured body temperature, which is quantitative. So we're looking at the mean temperature. So that's going to be mu. So far today, we've only used mu, but in your homework, you'll get to use some other population parameters. So my population parameter is mu. Mu is the mean body temperature for all healthy adults. Remember, it's a population parameter, so we should have the population somewhere in the description. All right, and then my sample statistic is going to be an X bar, and I'd have to actually look at the data to figure out what that is. And I did realize that I didn't put that on your notes page. So I'm going to go back to stat key and see if we can figure that out. So this data set is also in this drop down menu here. So I've got the body temp for 50 people, temperature is what I'm looking at here, and the mean body temp is 98.26. So I need to update my notes pages because that should be on there. It should be 98.26. So back here, let's say X bar is equal to 98.26. And this sample statistic is the one that we want to use when we're constructing our confidence interval. Well, if we were doing the standard error method. You don't actually need it when you're doing the percentile method. All right, so now we're going to find a 99% confidence interval for body temperature. So first thing we need to do is we need to look at how many samples we have, and we need to look at our confidence level and figure out how many dots to count. So take a second, not very long because our class is almost over, but take a second to see if you can figure out how many dots we should be counting for this example. Perfect, we're gonna have 10 dots. So we're gonna take the number of samples, 2,000 times 1 minus 0.99, which was our confidence level, divided by 2. So when you work all that out, you end up with 10 dots. So starting from the left, I'm gonna count over 10 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm about right here. I'm going to do the same thing on the other side, coming in from the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not very good at drawing straight lines on a computer. Okay, and where these values cross the x-axis, that is going to be my upper and lower bounds for the confidence interval. So looking here, I can see that there's like 0.1 of a degree in between here. These numbers seem slightly off of the center when I'm looking at my grid lines. So I'm going to call this one 97.96. And I'm going to call the upper one 98.56. So that's going to be my confidence interval, 97.96 to 98.56. So I would say we are 99% confident that the true mean body temperature for all healthy adults is between 97.96 and 98.56 degrees. And something that I think you'll get a chance to do this a little bit in your homework, but you can kind of play around with, is what happens to your confidence interval when you change the level of confidence. So I'll just give you a little preview here. Okay, so here's this body temperature data. If I click on the two-tailed button, right now it's at 95%. Watch what happens to my upper and lower bounds if I change this to a 99% confidence interval. So you can see that my confidence interval, you can see the red part got smaller, so my confidence interval got wider. And if I go the other way and put in 0.90, ooh, now you can see that my confidence interval got narrower. So the more confident I want to be, it's a trade-off. Then that makes the width of my confidence interval wider when I'm more confident. The range of plausible values. And the range of plausible values can be smaller if I have a lower level of confidence. So it's a trade-off. You can get a smaller range of values, but you're going to be wrong more often.